So let's now look at the second example. This is the vertical circle, all right? So this is probably, I think every kid has played with this before. If you go grocery shopping, you put something in a plastic bag and you want to swing it in a circle, right? So let's analyze the physics of it, right? So you swing something in a circle. Again, let's simplify instead of like grocery bags and apples and oranges inside. Let's just have a rope, right? And connect to a mast like this. And see, what I really am curious is about what is the minimum speed I need to swing this for this to maintain a circle. And you probably all had that experience of if you don't swing it fast enough, all your groceries just fall out of the plastic bag, right? So what's the minimum speed? I'm curious of that. Let's analyze some of the physics first. So this ball will sort of go around a circle. At some point it's here, 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 like that, right? This is very symmetric. I'm just going to draw here. Draw one side. But what's interesting is I think everyone noticed if you play with that, if you've done that game, right, the tension is not the same everywhere, right? It's not very democratic how the tension is distributed. So which point is the tension largest when you swing the object around? At the bottom, right? And the tension is weakest at the top. If you swing it just up, so that it just crosses the top like that, then the tension is almost zero over there, right? So what I'm curious is the minimum speed to maintain a circle. Okay, but let's analyze this, right? So let's start with drawing the free body diagram. Over here, let's pick these three places. Now, the free body diagram looks different at every point. Over here, what is the contact force? Well, there is a tension, okay? And what other contact force do you have? That's it, right? But there's also non-contact force, which is the weight. Okay, so I have two forces over here. And so this time, what's causing this to go in a circle is actually the combination of the weight and the tension. Both of these are causing the centripetal force. So let's call this at point A, at point B, and at point C. Right? At point A, the centripetal force, right? All the centripetal force is actually W plus T. Okay. So now if you contrast that with at point B, what is the tension? Well, the tension is up, right? When you swing the rope at the bottom of this, that's where the tension is largest, but the weight is going down. So at point B, the centripetal force is actually T minus W, right? Let me put this the other way around to contrast this, right? So this is the force that is causing it to go in a circle, right? However, the weight is working against you. That's not trying to go in a circle. So what you need is the complete thing that is causing it to go in a circle is this subtract by the weight. Okay, just from the diagram you can see basically centripetal. So this is emphasizing on the fact that centripetal force is not a type of force, but it's not like a specific force, I should say. It's a whole class of force. It's basically the amount of forces that is going towards the center. So what are the forces towards the center? It's this plus this. What are the forces going to the center? It's this minus this, because this is going down. Okay, and over here, just to show you that the situation, the free body diagram changes. The weight goes downwards, right? But the tension goes here. So at point C, what is the centripetal force? What is the part that is causing it to go in a circle? It's just T. Okay, W isn't even part of the equation over here. Okay, so if I'm curious about why the tension over here is the least and why the tension over here is the max, right? If I want to analyze the physics of that before I get to the minimum speed, then I can rearrange to solve for T. But remember the first step, identify your centripetal force. The second step, equate that to mv squared over r. So what does that tell me? If I want to solve for T, if I want to find out what's going on with the T, then this is mv squared over r minus W. This, right, equate this to mv squared over r. Try to memorize this. It will be very beneficial, right? So T is equals to mv squared over r plus W. Okay, so what's W? Let's actually over here plug in the formula, right? Since we're in the second step. While we're in the plugging in formula business, let's plug in more than one formula at the same time, so it can be a little bit more efficient over there. Now, before I even get to C, you see what is the tension? The tension at point A is just it's mv squared over r minus mg. But what are constants? Does m change throughout this whole motion? No, the mass stays constant. Okay, so the mass doesn't change. The r is the radius, so assume you are able to maintain a circle around there, then the r doesn't change as well between point A and point B. mg doesn't change. G is a universal, well, not universal, but on Earth, it's the acceleration due to gravity of Earth, and that is always constant on Earth. And V, is that a constant? Yes, it is by definition of uniform circular motion. I should add uniform over there, but yeah, we've mentioned that. We're talking about going in constant speed. So if you maintain the constant speed going around, can you see which tension is larger? Yeah, obviously, this is a smaller tension than this one. So at point B, you will have a larger tension, right? And then you can contrast that with this as well, with point C, mv squared over r equals to T. And again, m is a constant at every single point. R is the same, and V is the same at everywhere. So the tension here at point C is somewhere between the largest part and the weakest part. Okay? All right. So what's the minimum speed to maintain a circle? Well, over here, you know that where's the weakest point? The weakest point is over here, right? That's the part where if I don't have enough speed, I will fail to maintain a circle. So what if I have higher speed, what will happen? If I spin it very, very fast, then V will increase. V will increase. That just means, well, what can I change, right? R I cannot change. M I cannot change. G I cannot change. So the only parameter, the only thing I can really play with is the V. That's the only parameter I can play with. And what will that change? If I increase the speed, I will increase the tension in the rope, right? So what is, so that makes sense, right? If I spin very, very tightly, right, then the tension would get larger and larger until if there's a breaking point, then it will break. But that's not what we're concerned. We want to find not the largest possible speed, but I'm concerned about the minimum speed. So what's the minimum value of the tension? Can it be 0.1 newtons? Can it be 0.1 newtons downwards? Yeah, if you spin it very slow, you can at a point it's 0.1 newton. Can it be 0.001 newton? Yes. Can it be 0 newtons? Can T be 0? Yes, right? It's sort of just go above it, then at that point there's 0 tension, and then there's tension again as you let's say goes this way, right? So then you have tension again, and at the bottom you have tension again. So it can be 0. Can it be negative? What does that mean? Can this go negative? Well, if that goes negative, it means tension points upward. But the rope will never do that, right? And the rope will never stop pushing the object upwards. The tension always ropes always pull things. So no, so the minimum value of this, so T min is 0. All right. So if I want the minimum value of this, so I want the smallest possible of this, but the smallest value over here is 0. So I need to solve this equation when TE equals to 0. So that's what we need to solve, right? And now it's just a matter of rearranging this, right? So I have mv min square over r equals to mg. If I move that to the other side, the m's cancel, so v min square equals to g times r. V min equals to plus or minus square root of gr. What does the plus or minus mean? well, should I take plus or minus? First of all, this is just numbers, right? You can plug in whatever the rope length is as your radius. G is 9.81 or 10 if you're estimating, take the square root. But now you have two answers. Can it be negative? Excuse me. No, right? Because it's a speed. Yeah. So it's, if you're talking about that, like I said over here, this is always the speed, the v squared. Because if you're talking about velocity, it's constantly changing. The speed is uniform around the motion. Okay, so you can reject the negative number, and that basically is the minimum speed. Okay, all right. So we have looked at a vertical circle. We understand why the tension is different at every point. You can also try to figure out, right, if the maximum tension is 6 newtons, if that's the maximum tension the string can hold. If you buy a string, it'll tell you what's the maximum tension it can sustain, right? And now you can plug in some numbers. I haven't worked this through, but you can give it a try, right? So if you tie something to a 2 kilogram mass with a length of, let's say, 1 meter rope, what is the maximum speed you can spin things at? I can flip this around, and it's another question I can ask. Instead of the minimum speed to maintain a circle, what's the maximum speed I can do? I can play with this and not break the string, right? Still maintaining a minimum circle. Now, which point will you want to analyze for maximum? If you want to find out the maximum velocity, do you want to analyze this point, or this point? Well, the string will break. Where's the weakest point? Where's the critical part that we should analyze? Here, right? Because that's where the tension is max. If you calculate the maximum tension here, the tension will always be larger at point B. It's always larger than whatever the tension is at point A, because gravity here is sort of releasing the tension from the, so you need to maintain the circular motion, you need certain amount of mv squared over r, right? That's the amount of force you need to maintain a certain velocity and of a certain radius with a certain mass to go in a circle. So that's what centripetal force means. Here, you need, the weight is sort of relieving part of the T in order to provide that centripetal force. Here, the weight is working against T, right? T is trying to maintain a circle, but weight is trying to pull it away. So you kind of need more T over here. But there's a maximum that the string can hold. So you want to analyze it over here. So you want to find out what's the, if the max, so what you can do is put in max and max, because velocity is the only thing you can tweak like this, okay? So now you can find out, plug in all the numbers I've given you, and you can find out what's the max speed you can sustain if the string can sustain 6 newtons of tension, right? And it's also a good exercise to calculate what the period is. I won't use capital T because I just used that, but what is the period? What is the frequency? So how many cycles does that mean after you calculate the maximum velocity, or even with the minimum one we just did, right? This is in some sense more physical because it's easier to measure. If I ask you how fast, if I ask you to swing something at 2 meters per second, you will tell me, it's better if you tell me how many revolutions per second, right? So I can count in 1 second, this went 3 revolutions or 3 cycles, then it's easier to count. So these two are very frequent quantities we talk about in circular motion. Okay, so far we talked about a vertical one, a horizontal one. Let's quickly look at one where we combine both vertical and horizontal and see how we can analyze that.